Hello and what's up, everyone? Welcome to day 2 of our final review. This is our review for the final end of the year. We're almost there, and this is day 2 of 5. So let's jump right into it and start with a circle problem. We're reviewing circle parts right now, right? So we have the circle and we have a bunch of lines cutting through this circle, right? And we want to start off with A. It says center of the circle. So every circle has one and only one center. And the center of this circle is just like the rest of them, it's a point. And this one is named point F. We're going to put point F. Next up, we want to name a chord. Now, there's a couple different chords going on in this circle. A chord is a line that goes across our circle. Its endpoints are on the circle, but it doesn't go through the middle. So a chord here, for instance, G, C is a chord. Now, a chord is a line segment, not a line necessarily. So GC is a chord. And then we also have ED. ED is also another chord here. And this is line segment GC, line segment ED. I'm going to rewrite my G's. Kind of sloppy. There you go. GC, ED. Next up is a secant of the circle. Now, a secant is a line that cuts through the circle twice. We have one secant here. And notice I said a line, not a line segment. So we only have two lines here. We have line AB right here. We could tell by the arrows at the end. And then we have line GE. But notice that GE cuts through our circle twice. So GE is our secant. The tangent is where it touches once, and that's going to be AB. Once again, a tangent line is a line. So we're going to put line A, B, and notice they have the arrows up top. Next up, the point of tangency. Where does this line touch our circle? That's going to be at point A. So at point A, this line AB touches our circle. Central angle. A central angle is just an angle located at the center of our circle. We have two of them here. We have GFA, we can say angle GFA, and also angle GFE. GFE. And what we notice about both those angles is they're right angles. Next up, an inscribed angle. An inscribed angle is an angle whose vertex is on the circle, and then it goes across the circle. So for instance, one inscribed angle here is AED. So we can say that AED is an inscribed angle. We have a couple of them here. So AED. We also have GEA. Oh, I forgot my angle symbol. Angle GEA. And also, we have angle GED. Cool. Next up, H, we have an arc. So there are a bunch of different arcs. Arcs are just parts of the outside of our circle. So we have arc AC, we have arc CD, we have arc DE, we have arc EG, we have arc GA, and we got a bunch of different other types of arcs there. But these are different types of arcs. So I'm just going to say, hey, arc AC. Boom. We have arc CD. Boom. Arc DE. I'm just going to give a couple examples here. Boom. Now it asks for a major arc. And a major arc is an arc that goes more than 180 degrees, or an arc that uses more than one point. So it's made up of multiple different arcs. That's one way we like to describe the arc here. So one example of that would be GCE, let's say. GCE would start at G, go around to C, pass it though, and we stop at E. So it's most of the circle. So that's an example of a major arc, G, C, E. And a minor arc is just an arc that's smaller, right? For instance, GE. GE is a minor arc. 2 points, less than 180 degrees. Next up, we want our diameter. And diameter is a line that cuts all the way across our circle and goes through the center. We have one diameter here, and it's going to be AE. Line segment AE is our diameter. And last but not least, semicircle. Semicircle is half of the circle. So a semicircle here would be AE. Either way we go, it's going to be AE. That's half of our circle. But we're going to call that arc AE. Arc AE is a semicircle. It's an arc that's half the circle. Awesome. So there's a little brief overview of circles and parts of a circle. If you're confused about any parts of these, I suggest typing them into Google, looking at the images. If you go to mathisfun.com, they got a lot of good resources there. Or don't be afraid to ask me or your teacher for help or to clarify anything I've stated here. Next up, we have some more things with the circle. But now it's just differentiating between inscribed angles or central angle. And that's all we want to say. So XWR, we have XWR. That is this angle right here. And what we notice about that angle right there is its vertex is at the center of the circle. So that's what we call a, central angle. VST. VST. Where's the vertex there? VS is our vertex, and it's on our circle. So that is a inscribed angle. VWU. 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 VWW is our middle of our angle. So we want to say that is my central angle. Next up, XRU. XRU. I'm going to leave that for you guys to decide. Is that an inscribed angle or is that a central angle? And for the next two, I'm going to leave those for you guys to decide also. Are they inscribed or are they central? Remember, inscribed angles, the point or the vertex will be on the circle, on that outside, and the central will be in the middle of the circle. Keep that in mind. Get these three done. Next up, we want to use our inscribed angle theorem and central angle theorems to decide the measurements of each of these units. Well, what we know about our first one, which is an inscribed angle, is that the inscribed angle here is half of this arc. So we could say that angle STU is 1/2 of arc SU. So what's the measure of arc SU? It's 198. So we could say that angle STU equals 1/2 times 198, which is going to give us 99 degrees. So angle STU, the answer here is B. It's at 99 degrees. Should be the measure of angle STU. Next up, angle RPU. Well, notice RPU, this is going to be a central angle, right? So we have to use our central angle theorem. Our central angle theorem states that the central angle is equal to the arc that it intercepts. So this is our arc here. It's 30 degrees. So our central angle here is going to be 30 degrees. But notice RPU is the combination of these three angles. So we have to add them up. 30 plus 75 plus 45. 30 plus 75 will give me 105. Plus 45 will give me 150 degrees. Also known as A. Next up, they want to know the measure of arc MN. Where's MN? MN is right here. And we need to think about how can we figure this out? We don't know any of these angles here. But we do know a couple things, right? We could tell that this angle and this angle looks like they're vertical angles, which means that these two angles are equal. This angle we know is 75 because the arc is 75. This is a central angle, which means that this angle would be 75 degrees, which means our arc would be 75. But what if these aren't perfect lines, mister? Well, hey, we have another way we could figure this out. We could say that JKM, right? JKM or JM, arc JM is a semicircle, also known as half of a circle. So what we could do is we could say that's going to equal 180 degrees because that's half of a circle. Half of a circle is 180 degrees. So we could then do 75 plus 50, which would give me 125. And we could find this chunk here by saying 180 minus 125, which will give me 55 degrees. But that's not what we're looking for. We're looking for here, mister. Well, we also know that KN is a semicircle. So if KN is a semicircle, 50 and 55, we add those together would give me 105. 180 minus 105 would give me 75. So once again, we could verify that this arc will be that 75 degrees. And I showed you two ways to find it, either using vertical angles or by using the idea of semicircles. Awesome. Next up, they want to know what is the angle measure of PRQ. And we have two. For the first one, we want to know PRQ. For our second one, we want to find the value of X here. But this is using our exterior angle theorem. And what that states is that this exterior angle here, NPQ, is the exterior angle of a triangle, is the sum of our two remote interior angles. So the two angles inside the triangle that are not touching it, right? So in other words, what we could write here is angle NPQ is equal to angle PQR plus angle QRP. And what we know is NPQ is 115 degrees. PQR is 70 degrees. And we don't know QRP. Or, sorry, let me rewrite that. PRQ. We're keeping it consistent with the question here. PRQ. We don't know that. So what we could do is subtract 70 from both sides. And what's that going to give me? That will give me 45 degrees equal to angle PRQ. Awesome. Cool. So next up, we want to use that same theorem, but now we're working in reverse just to find the outside, right? So once again, we could say that this exterior angle, BCD, angle BCD, which is our exterior angle here, is equal to the two remote interior angles. So angle BAC plus angle ABC. We know BAC and we know ABC, so all we have to do is say angle BCD is equal to 45 plus 65 degrees, which is just going to give me angle BCD, is equal to 110 degrees. And there we go. Let me just box off my answers here. Sorry. Whoops, how did I do it twice? There we go. Boxing off. Box it off. There we go. And to our next one. It's asking us what is being constructed in each image. So we have pictures of constructions. Now think back to earlier in the year, and some of us may have done this if we were in a classroom, and some of us may have not if we weren't in a classroom due to the pandemic. Constructions, we used a compass. If we weren't in the classroom, we did this online most likely, and we used a virtual compass. Maybe some of us did it that way anyway, but we may have done it in person on a piece of paper. Now, we want to know what is being constructed. Well, in my first one, this construction is cutting the line segment in half, AB, and it's giving me a perpendicular line. So what we could say is this is a perpendicular bisector. And my next one, we see that we have a line coming out of an angle, and this is called our angle bisector. And what this is telling us is it's cutting this angle in half. So ABC, it cuts in half. ABD and CBD are equal to each other. That's an angle bisector. Next up, It says determine whether it is possible to form a triangle using each set of segments with a given measurement. Explain your reasoning. Well, this we could use our Pythagorean theorem. Now remember, our Pythagorean theorem is a squared plus b squared equals c squared. And in this Pythagorean theorem, we just say, hey, the biggest number has to be c, and that means these could be a and b. It doesn't really matter. And if we plug these numbers in and they are equal, each side, the left and the right, then we're good to go. So we get 5 squared plus 7 squared equals 10 squared. Give me 25 plus 49 equals 100. What is 25 plus 49? I can tell you one thing, not going to be 100. That's going to give me 74. Does not equal 100. So not a right triangle for my first one. There we go. Next up, let me change my color. 8, 12, and 15. Remember, Pythagorean theorem, a squared, b squared equals c squared. C has to be the biggest number. A and b could be either of the other two. I just like putting them in order. We got 8 squared plus 12 squared equals 15 squared. 8 squared gives me 64 plus 12 squared. Let me just double check. I think it's 144. It is. Equals 15 squared. I want to say it's 225, which it is. 225. Now we just have to add 64 plus 144. Do they equal? No. This is going to give me 208. And that does not equal 225. So not a right triangle. And there we go. Next up, we just want to list our properties of each of these shapes. So what makes them what they are? Well, all of these are quadrilaterals, so we do not have to say they have 4 sides. But I'm going to put it here anyway, right? So 4 sides, 4 sides, and 4 sides. What makes a rectangle a rectangle? Well, the only thing, we have a couple properties here. Opposite sides are equal. And all angles are 90 degrees, aka right angles. That's what makes a rectangle a rectangle. A rhombus is going to have all sides are equal. And last but not least, this is going to combine the two. All sides are equal and all angles are 90 degrees. There we go. We got our square. They're like the baby of the rectangle and the rhombus. All right, last problem. Consider the construction of a regular hexagon inscribed in a circle. Which of the following statements is true? Select all that apply. First one says the radius of the circle is equal to the length of the arc between the consecutive vertices of the hexagon. This is not true. The second one says a central angle formed by 2 consecutive vertices of the hexagon and the center of the circle would measure 60 degrees. This one's easy to figure out. We know a hexagon has 6 sides. That means that's going to be creating 6 angles on the inside if we connect the vertices. 360, which is a full circle, divided by 6 would give me 60 degrees for each available angle. So B is an answer. That's 1. The sum of the lengths of the sides of the hexagon is equal to the circumference of the circle. That also is not true. It just wouldn't work out because think about it. The hexagon's on the inside of the circle, which means it's connecting different parts of the circle, cutting out all that outside, so that does not work. And the last one, the side lengths of the hexagon are equal to the radius of the circle. If we did this, this would also be true. One way we could tell is since the central angles are 60 degrees, it means all these angles are 60 degrees created within this hexagon, which gives us equilateral triangles. So if we had this hexagon in there and we drew lines coming from the center to each vertice, it would give us a bunch of equal triangles. And equal triangles, which the lines going from the center to the outside would be the radius, and then the lines connecting those radiuses would be the sides of the hexagon. They are all equal, which means that this statement is true. Awesome. Now, that is all we got for today. I hope you guys learned a little bit something, remembered a little bit more, and don't be afraid to ask questions or ask for help if you're confused about any of this. And see you next time. Peace.